Hello, in this lesson, we are going to discuss in continuation to the types of chemical reactions. We have already discussed combination reactions, decomposition reactions, types of combination reactions, types of decomposition reactions. We discussed thermal, we discussed electrolytic, we discussed photolytic. There are multiple more examples that you can see online, you can see in multiple different books, but we need to remember at least the important ones, which is very much important from the general course point of view. So the third reaction that we are going to start with right now is displacement reactions. So from the term itself, displacement, that means something is getting displaced. So we can write this way that if you have any metal, so here. So this can be a simple one. So if you have, you can say any kind of compound AB. So this is our metal which is displacing A. So it's kicking off A and it's making its own compound, and this metal is getting displaced, right? This is also metal. So this will be metal displaced. So how we can define it? Displaced, replaced by any other atom or a group of atoms. So we can say that displacement reactions are chemical reactions in which an atom or group of atoms in the molecule or compound are replaced by another atom or group of atoms. That is what we call displacement reaction. So A is a metal displaced, and we can even say this is a leaving group. Now, we are going to study first displacement reaction of metals. So, we can say in this, since we are talking about metals, in this, a highly reactive metal displaces the less reactive metal from its salt solution. So before moving to this, you can say displacement reaction of metals, and before moving to the examples of this, we need to remember something. We need to understand the relative reactivities of metal. For that, we have to understand a little bit about reactivity series of metals. We even call it as activity series of metals. So it starts from the most reactive metal, potassium, then sodium, calcium, barium, magnesium, aluminium, zinc, iron, nickel, tin, lead. We are keeping hydrogen. There is a reason behind it that we will be discussing. Copper, mercury, Ag, that is silver, gold, platinum. So the whole reaction, you can say the reactivity order, the reactivity decreases in this order. So this potassium over here is the most reactive. Then these all metals above hydrogen, these are more reactive than hydrogen. If we talk about till here, right? Then if we talk about after hydrogen, these are metals less reactive than hydrogen. So this is going to be least reactive. And gold and platinum are very much noble metals. So what's the meaning of this entire series? Why it is so important? So let's try to make a reaction. If I say iron, iron is over here. It reacts with copper sulfate. Copper is over here. So iron reacting with copper sulfate to give us what products, how we can understand it. So iron is more reactive than copper. So any metal more reactive than the other metal in this series has the capability to displace that metal from its salt solution. So iron can kick off this copper from its salt solution, make its own salt FeSO4, and copper is, you can say, kicked out. So this is copper is a replaced metal over here. Iron is the one which is replacing it. That's why we call it as displacement reaction. Now if we do the opposite reaction of this, copper reacting with FeSO4. So we know copper is less reactive than iron. Iron is more reactive. So we know copper doesn't have the capability to kick off iron from its salt solution. So this reaction will not take place. So no reaction. So you can say this kind of reaction is non-feasible. That means it cannot happen at the first place. The first one is feasible. So we can make multiple, you can say, reactions from this particular series, and we can understand which metals can replace other metals from its salt solution and which cannot. So anything above hydrogen can react with, you could say, water, can displace hydrogen from its acid. Anything below hydrogen, copper, mercury, silver, gold, and platinum generally do not react with water and do not have the capability to replace hydrogen from its acids. So copper can react with nitric acid, dilute in concentrated form, but that is not the usual behavior that we see. That's again, you can say it's not commonly seen that copper reacts with acid. You can say at least the sulfuric acid doesn't, but yes, this reaction can happen. I'm writing out of the blue over here, so this you can write it as a simple note. That's not a type of displacement reaction, but these reactions are very much important. So copper reacting with HNO3, this is nitric acid. It's a very strong acid. So in the dilute form, there are two reactions which I'm going to write. In the dilute form, what particular products it's going to give. It's generally going to give us more or less same, except for the nitrogen oxide over here. So concentrated. So in case of dilute, in both cases we are going to get the same salt, copper nitrate. To be more precise, cupric nitrate, or copper with the charge +2 nitrate. So along with along with water, And in the case of dilute, we will get nitric oxide. In the case of concentrated, we will get NO2. So in both cases, rest everything is same, just the oxide of nitrogen is different. And we know nitrogen dioxide, brown fumes. This is the most important reaction. Most of the time, they try to ask you which oxide of nitrogen is formed when copper reacts with nitric acid. Now, there is another story to it. Copper is a metal. Metals reacting with nitric acid will give you a salt, and we know when metals react with acids, they will give you salt and hydrogen gas is released. But in this case, if you can see, water is getting released. Now, what will happen over here? Since nitric oxide is a very strong oxidizing agent, it oxidizes hydrogen into water. Now, what is oxidizing agent? That we can discuss in redox reactions, but at least as of now, if you can remember these two reactions, which are quite important ones, that copper reacting with dilute nitric acid, then what it is giving us nitric oxide, copper nitrate in water. These are same products in both the equations, but with the concentrated, it's giving nitrogen dioxide. So then we go to the next one, that is displacement reaction of non-metals. So for non-metals, we don't have many varieties of chemical reactions under this. It's definitely displacement. So we will follow this reactivity order. We are not going to add many non-metals. We don't even have many non-metals in the periodic table. We are just going to add these four over here, and they belong to the very famous 17th group elements. If you can see in the periodic table, if you have in front of you 17th column, that's your left to right. If you go the 17th column from top to bottom, if you see, we call it as a group. So it starts from fluorine, chlorine, bromine, iodine. So these four elements I'm talking about. We are not talking about the elements beneath. So over here, let's write a reaction. If you have sodium bromide reacting with chlorine. So according to the above reactivity order, we can see chlorine is more reactive than bromine. So it's going to kick bromine out of this particular solution, and it's going to form its own salts. This is aqueous, this is gas. So we have NaCl and bromine is going to be released. This is aqueous again. So this is displacement reaction. So non-metals, highly reactive non-metals only can do so. Now if I reverse this equation, NaCl, and if I have taken bromine, then no reaction will take place. Why? Why? Because we have bromine over here. Bromine is less reactive than chlorine, so it won't be able to displace chlorine from its salt solution. So no reaction. So I hope you are clear with this. Then we go to the next reaction. Double displacement reactions. So in this mutual exchange of ions takes place between aqueous solutions of different compounds. Now we discussed before, double displacement reaction can be of two types. So there is mutual exchange. So the line that you see over here in between, this is the chemical bond. So AB reacting with CD will give you AD, and BC. So if you can see, there is some exchange happening. A is reacting with D over here. So if we write this hypothetical format of the double displacement reaction, remember the one which I have written on the left hand side is a metal, is electropositive. Or if we don't say metal, it's electropositive, and the right hand side, that means right hand side is electronegative, carrying negative charge. So A over here is carrying positive charge, B is carrying negative charge, C positive, D negative. So opposites are going to be attracted towards it. A, since it's positive, it will be attracting D negative. B negative will be attracting C positive. That's what how it's done. So we'll understand better through an actual chemical reaction. So under this we have precipitation reaction. So if we say precipitation is a type of double displacement reaction where you have one of the product as insoluble substance, in which one of the product is a precipitate. It's an insoluble substance which is going to settle at the bottom. So if you have a test tube, right, so the precipitate is always going to settle down at the bottom, and the short form that we use for precipitate is PPT. Precipitates can be colored, can be white in color, can be colored, can be different other colors also. So let's have an example over here. So we have this reaction, silver nitrate, a very important reagent in chemistry lab. Silver nitrate solution, its aqueous form we have taken, and then we have taken NaCl aqueous form. So they both are reacting to give us what? So Ag being positive is going to react with Cl, if you can see, and it's going to form AgCl, silver chloride, and sodium nitrate is formed. Now AgCl is a white color precipitate, white PPT, and this is aqueous, means sodium nitrate is very much soluble in the aqueous solution. So how are you going to do it? You're going to take 3 test tubes. In the first test tube, you are going to add silver nitrate solution, like a pinch of it. You can measure it as few grams, but even if you just take small pinch, it's okay. We don't have to be so, you can say, so much precise in terms of the amounts that we're going to, because the amounts that we're going to take over here, because we don't, we just need to see the white precipitate. If it's getting formed, then our, you can say, experiment is success. So AgNO3 is like you take some pinch of that, it's a white color salt, pinch of salt, and put it in the test tube, put some water in it, and then in the second test tube again do the same thing, take NaCl, pinch of that salt, it's a white color salt, put it in water. Then in the third test tube you add the component of the first test tube and the second test tube. You will immediately see some precipitate at the bottom. This is your AgCl precipitate, white color precipitate. Now, how we have to remember, we don't have many precipitate reactions in chemical reaction and equations, at least of this level, but whatever precipitates that we are studying, few 4 5 examples that we need to memorize. And most of the silver salts, AgCl, AgBr, AgF, AgI, these all are insoluble in water, and they are called as precipitates. So moving ahead, so remember that why they are forming compounds like this, Ag plus will be attracted towards what? Cl minus, right? NO3 minus will be attracting towards Na plus. So it's mutual exchange of ions which is happening in the aqueous solutions. That's what I wrote as a definition over here. Then we go to next example. We are going to take aluminium chloride, aqueous solution, and ammonium hydroxide, again aqueous solution. So this is a perfectly balanced equation. Okay, so if I forgot some balancing part in the previous equation, please feel free to do so on your own without my help. I hope you can do it, and I'm very sure, certain of this that you can do it. Okay, so aluminium chloride reacting with ammonium hydroxide. So what product we are going to get? We are going to get aluminium hydroxide over here. This one. So aluminium hydroxide. Now the formula. If you are still not thought over the formula, go back to the basics part. Not the basics. This is the entire basics only. The previous lectures where I've taught you the chemical formulas in the ions chart. So we will get another product, ammonium chloride over here. Ammonium chloride is aqueous. So everything is aqueous. But aluminium chloride, aluminium hydroxide formed over here is a precipitate. So it's again a white precipitate. So we need to balance this part. We need to have three. How do I know? See, in these kind of radicals where it's very tough to balance, you look at it like the radicals form. So how do I know it's three over here? So what we can do? This is like three OH groups, right? I can see three OH group over here. So I'll put three, right? Hydroxide is balanced. Aluminium is already balanced. So if we put 3 in front of this ammonium chloride, 3 ammonium. So these are 3 ammonium and 3 chloride. So it's perfectly balanced. 3 chloride, 3 ammonium. So take it as in the radical form. Don't try to take it as an individual. If you have these kind of equations, double displacement or precipitation or neutralization reaction. So try to look at them in the form of radicals, how many radicals you have on the left and right hand side. That will make it a little easier. If you see individual atoms, then it might mess up in your brain and you won't be able to answer it properly. Then we can take some more examples. We are going to take our favorite silver nitrate again. See, why silver? Why silver nitrate? There is silver in that. Silver, if it is going to form most of the precipitate, chloride, bromide, iodide, fluoride, then why not silver nitrate? It's a very important reagent. So silver nitrate, aqueous, it's going to react with sodium iodide. So again, what's going to happen? We are going to get silver iodide over here. If you can see AgI and what color it has. It has yellow color, yellow precipitate. Plus NaNO3, which is very much soluble in water. So it's a perfectly balanced equation. So remember, AgCl is white PPT, AgBr is creamy, AgF is pure yellow, people say, or yellow. AgI we just did, yellow. At least this you can remember. Now next example that we're going to take is sodium sulfide. One of the reactant that we are going to take. Now we're going to form a sulfide over here as a product. And it's going to react with lead acetate. Lead with the charge 2 plus. So they both react. Again, they are both aqueous. If I forget to write, please, these are aqueous solutions only. one of the product on the on the product side is going to be solid. And one more thing, the precipitates are always in the solid state. State of matter for precipitate is always solid. It's never aqueous. Because if it's aqueous, then what's the difference? Okay, so we have now again what product we have. So sodium is a cation over here, and the anion that we have over here is the acetate. So we are going to form the product sodium acetate, CH3COONA. Na plus CH3CO minus. That's a formula. That's why the formula is CH3CONA. Both are monovalent, you can say cation and anion. Now, this I might have told you in the chemical formula uh, lecture that acetate is going to be written as the first, and metal we are going to write on the right hand side of the formula like this. That's a rule because this is organic. Most of the inorganic compounds will have metal on the left hand side, non-metal on the right hand side. So we are having sodium acetate, which is very much soluble in water, and then we have lead sulfide, PbS. Lead sulfide. So this is again solid, and this is black precipitate that we need to remember. Most of the sulfides are black, not always, but most of them, yes. Now we need to balance this. So we can see that we have two sodium atom over here, two. So if we need to make this two, I need to put two coefficient in front of this. Then this acetate is already two over here. This is balanced. PbS is balanced. So I think rest everything is balanced over here. Now we move to the second type of double displacement reaction, that is neutralization reaction. So neutralization, from the term itself, something is getting neutralized. So we have our acid reacting with base to form salt and water. This is a typical example of neutralization reaction. So I'm not going to deal much in depth for neutralization in this lecture, but in the future acid basis salts we will be discussing in depth. So acid, HCl, base, NaOH, sodium hydroxide reacts to give what? The salt, NaCl, and water is formed. So it's a perfectly balanced equation. And do remember, when we talk about NaCl, salt, so salts are formed from the cation of the base. The base over here is this sodium hydroxide, and anion of the acid. So in this also there is mutual exchange of ions taking place. That's why we can call it as double displacement reaction. And most of the neutralization reactions are exothermic in nature. That means heat energy is released. There are multiple types of neutralization reaction that we can discuss in acid basis salts. So remember one thing, if you see any kind of acid, if there is a hydrogen, that means it has a capability to release H plus ions or hydronium ions in the presence of water. So we call it as an acid only because of this HCl. If you put it in water, HCl is manufactured in the form of gas initially, so it will form H plus and Cl minus ion. So this H plus will immediately react with this water and form hydronium ions, and this is responsible for the acidic properties of any acid. Similarly, if we talk about base, NaOH, in the presence of water, it will give you Na plus and OH negative ion. This is what we say hydroxide ion, and this is very much responsible for the basic character of bases. So acid and base both neutralize their effect to form salt and water.